The non-trivial weight tuning process is arduous yet unavoidable procedure in MPC design. It comprises of a suitable selection of weighting parameters that reflect the relative importance of each element within the underlying optimization problem. While the heuristic trial and error methods are adopted for this purpose in most cases, the resulting tuning process requires a skilled controller designer with a plenty of trial time and tuning experience with the system. Moreover, in practice, users prefer to conduct these trial and error methods either on a real robot or in simulation. Whereas the former might be dangerous, especially with aero robots, the latter requires an accurate system model. Therefore, in this work, we propose an active exploration-based methodology for MPC tuning. Furthermore, to avoid conducting the dangerous trial over the real robot, we incorporate a deep robot model in the proposed framework. We start with creating the deep quadrotor model utilizing the real operational data. This DNN model is then utilized within the simulation tuning of the framework. After having the DNN model, we continue with the tuning process. Each trial run starts with the trial configuration module. Within this module, weight set selection and stable flight mode submodules give necessary instructions to an MPC. Taking these as inputs, an MPC controls the quadrotor model while its performance is being observed simultaneously. Once the flight is completed, the performance of the NMPC with the utilized weight set is graded based on 5 criteria. Subsequently, the trial is finalized by updating the lookup table for the weight set cluster. Thereafter, a new trial begins with the selection of a new weight set within the trial configuration module and thus closes the loop. After obtaining the weight sets from simulation tuning, we employ the weight sets with the highest grade value for tracking sequential set point trajectory. As can be seen, the weight set obtained by tuning over the DNN model results in a precise tracking performance. In order to cater for various operational uncertainties that may not be captured in the DNN model, we also conduct real flight tuning. The overall tuning process remains the same except that the trials are now conducted over the real robot. The process starts with the hover flight mode, which continues for 10 seconds. Before proceeding with the next flight mode, we let the robot stabilize for a couple of seconds. Then, the robot tracks a single set point for 10 seconds. After stabilizing, the robot proceeds with multiple set points tracking for about 40 seconds. In this work, we repeated the real flight tuning for 30 episodes. Subsequent to obtaining weight sets from the real flight tuning, we again perform the trajectory tracking with the weight set having the highest grade value in the lookup table. As can be seen, this weight set also results in a precise tracking performance. Moreover, the overall tracking performance has improved due to the real flight tuning over the real robot. To conclude, in this work, we have proposed a novel active exploration-based methodology for MPC tuning. The results have exhibited that the proposed technique obtains flight-worthy weight sets that can be directly deployed on the real robots. Moreover, the conducted user-based study has manifested its superiority over the manual tuning procedure. For more details, please refer to the paper.